Hello and welcome to the science class. My name is Teacher John. I'm going to take you through science, primary 7, term 2. Primary 7, term 2. In our previous lesson, we looked at a machine and we said a machine is a device that simplifies work. We said we have two types of machines: simple machines and complex machines. We say simple machines are devices made up of few parts and simplify work. Then complex machines are devices made up of many parts and simplify work. Then we divided simple machines into 6 classes. We said we have levers, inclined planes, pulleys, screws, wheel and axle, and lastly, wedges. And we started by looking at levers. We also looked at parts of a lever. Then we said we have 3 classes of levers. We have first class levers, second class levers, and third class levers. So this morning, we are going to begin by looking at first class levers. What are first class levers? Now, first class levers are with the pivot in between the effort and the load. You can say okay, we shall say these are levers where the pivot is in between, the load and the effort. First class levers are levers where the load is in between. First class levers are levers where the pivot is in between the load and the effort. First class levers are levers where the pivot is in between the load and the effort. Then we have examples of first class levers. 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 1, we have a seesaw. Number 2, we have crowbar. Number 3, we have water pump. Number 4, we have lid opener. Number 5, we have a pair of scissors. A pair of scissors. A pair of scissors. Then we have claw hammer. We have a claw hammer. So these are examples of simple machines in the first class levers. Then we have pincers, and so on. So these are examples of simple machines under first class levers. So we want to draw some of these diagrams. We shall begin with a pair of scissors. A pair of scissors. A pair of scissors. Can draw it like this. A pair of scissors. Now, this pair of scissors, this one is called pivot. Pivot. This is the load. Then this is the effort. First class levers, pair of scissors. We have the effort, the pivot, and the load. So we say with first class levers, the pivot or the fulcrum is in between the effort and the load, or the pivot is in between the load and the effort. We say the pivot is the turning point. The turning point of a machine is called a pivot. So a pair of scissors, the pivot is in between the load and the effort. And that's why we categorize it under first class levers. Is that the first class levers? Because the load, the effort, no, the pivot is in between the load and the effort. Then we can draw a seesaw. We have a seesaw. A seesaw. A seesaw. So this is the load, then this is the effort. So we say first class levers, the pivot is in between the load and the effort. So this is a seesaw, so the pivot is in between the load and the effort. That's why we categorize a seesaw under first class levers. Then we have a crowbar. A crowbar. A crowbar. The crowbar this part is pivot, this one is effort, then this one is the load. So with a crowbar, the pivot is in between the effort and the load. That's why it is categorized under first class levers. Then we have a lid opener. A lid opener. A lid opener. A lid opener. This one here will be the effort. Then the lid will be the load. This will be the load. Then the pivot will be there. So the pivot is in between the load and the effort. The pivot is in between the load and the effort. This part is the pivot, then the lid itself is the load. So you find that the pivot is in between the load and the effort. That's why it is categorized under first class levers. Then we have a claw hammer. We have a claw hammer. A claw hammer. With a claw hammer, we also have the pivot in between the load and the effort. So that one is a claw hammer, and a claw hammer has the pivot in between the load and the effort. So that one is called a claw hammer. And this claw hammer, we have the load there. So this is the load. Then we have the effort. This is the effort. Then we shall have the pivot there. This part is called pivot. So this is the load. The load, pivot, then effort. That's what we are saying. A claw hammer has the pivot in between the load and the effort. We said first class levers, they have the pivot in between the load and the effort. So a claw hammer is under first class levers. As you can see, the pivot is in between the load and the effort. Then there are some things you need to know about first class levers. In first class levers, the effort arm is longer than the load arm. In first class levers, the effort arm is longer than the load arm. The effort arm is longer than the load arm. We say the effort arm is the distance between the effort and the pivot. Then the load arm is the distance between the load and the pivot. So we are saying first class levers, the effort arm is longer than the load arm. So from here up to here is what you call the effort arm. From the effort to the pivot is the effort arm. So it is longer compared to the load arm, the distance from the load to the pivot. So with the first class levers, the load arm is shorter and the effort arm is longer. And the advantage of using first class levers is that less effort is used. The advantage. What is the advantage of using first class levers? That's a question. What is the advantage? What is the advantage of using first class levers? What's the advantage of using first class levers? Less effort. Less effort is used to overcome the load. Less effort is used to overcome the load. Less effort is used to overcome the load. That is the advantage of using first class levers. With first class levers, when we use them, we use less effort. We use less effort to overcome the load. So this question is very important. You need to note what is the advantage of using first class levers. less effort is used to overcome the load. Now, if you look at when you are cutting a piece of cloth, a piece of paper, using a pair of scissors, you find that you use less effort to overcome the load. You cannot use a lot of energy to cut a piece of paper using a pair of scissors, because the pair of scissors has the effort arm is longer than the load arm. If you look at a claw hammer, the effort arm is from the effort up to the pivot. The load arm is from the load up to the pivot. So you find that the effort arm is longer than the load arm. And that's why we use less effort. That's why we use less effort to overcome the load. So if they ask you the advantage of using first-class levers, less effort is used to overcome the load. Why do we use less effort to overcome the load in first-class levers? That's the question. Another question. Why is less effort used to overcome the load? Why is less effort used to overcome the load in first-class levers? It is simply because the effort arm is longer than the load arm. It is because the effort arm is longer than the load arm. Because the effort arm is longer than the load arm. Why is less effort used to overcome the load in the first-class levers? Because the effort arm is longer than the load arm. So that is something we need to understand. Next, we look at second-class levers. Second-class levers. We have already looked at first-class levers. We look at second-class levers. Second-class levers. And with second-class levers, the load is in between the pivot and the effort. The load is in between the pivot and the load. So we shall say these are levers. These are levers where the load is in between, the effort, the load is in between the effort, the load is in between the effort and the pivot. So with second-class levers, the load is in between the effort and the pivot. So we look at examples of second-class levers. Examples of second-class levers. Examples of second-class levers. Examples of second-class levers. One, we have wheelbarrow. Wheelbarrow. Number 2, we have bottle opener. Bottle opener. Bottle opener. We have human foot. Number 3, we have human foot. Then number 4, we have a nutcracker. We have what you call nutcracker. 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 So these are examples of second class levers. We have a wheelbarrow, human foot, nutcracker, and a bottle opener. Those are examples of second class levers. If you look at page 46 in your book, there is a diagram showing a wheelbarrow, bottle opener, nutcracker, and the human foot. So we look at the advantage of using second-class levers. With second-class levers, the effort arm is longer than the load arm, just like first-class levers. Thus, the effort arm is longer than the load arm. And with the second-class levers, less effort is used to overcome the load. Less effort is used to overcome the load. And that's the advantage. So what is the advantage of using second-class levers? Second-class levers. The answer is less effort is used to overcome the load. Less effort is used to overcome the load, and that's the advantage of using second-class levers. We use less effort to overcome the load. So if you are pushing a wheelbarrow, carrying bricks on a wheelbarrow, you will use less effort. Why is less effort used to overcome the load in the second-class levers? Why is less effort used to overcome the load in second-class levers? Why is less effort used to overcome the load in second-class levers? So less effort is used to overcome the load because the effort arm is longer than the load arm. The effort arm is longer than the load arm. The effort arm is longer than the load arm. That's why less effort is used to overcome the load in second-class levers. As simple as that. The effort arm is longer than the load arm. That's why less effort is used to overcome the load. Let's see a nutcracker. Nutcracker. So that is the effort, this is the load, and this part is the pivot or fulcrum. So we say second class levers, the load is in between the effort and the pivot. And this one is called a nutcracker. It's called a nutcracker. So we look at third class levers, third class levers. Third class levers and third class levers are levers where the effort is in between the load and the pivot. These are levers. These are levers where the load, where the effort is in between, the load and the pivot. These are levers where the effort is in between the load and the pivot. Remember we said first class levers, the pivot is in between the load and the effort. Second class levers, the load is in between the pivot and the effort. Then in third class levers, the effort is in between the load and the pivot. So we look at examples of third class levers. 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 We have human arm. Human arm is the third class levers. Fishing rod. Fishing rod. Then we have a spade. We have a spade. We have tweezers. Tweezers are under third class levers, including a broom, a rake, all those. Broom, rake, they are under third class levers. Then we need to draw some of these diagrams showing third class levers. We shall begin by maybe before we draw, there's another one which I want you to add. It's called sugar tongs. Sugar tongs. Sugar tongs. So we want to draw some diagrams to show third class levers. Fishing rod. So this is the load on a fishing rod. Then we have the pivot or fulcrum. Then we have the effort. So a fishing rod is under third class levers because the effort is in between the load and the pivot. Where you hold when you are fishing, when you are holding the rod, that part is called pivot or fulcrum. And the fish becomes the load. So a fishing rod is under third class levers. Then we have a spade. A spade. So this is the load, this is the effort, then this is the pivot. So the reason why I said is under third class levers because the effort is in between the load and the pivot. As simple as that. Then there are some things we need to note about third class levers. One is that more effort is used to overcome the load, NB. In third class levers, more effort is used to overcome. More effort is used to overcome the load. So when you're using third class levers, you use a lot of energy because more effort. Okay, we use more effort to overcome the load in third class levers. The question is why? Why is more effort used to overcome the load in third class levers? Why is more effort? Why is more effort used to overcome the load in third class levers? That's a question. Why is more effort used to overcome the load in third class levers? Why is more effort used to overcome the load in third class levers? It is because the load arm is longer than the effort arm. We say load arm is the distance from the load, the pivot. The distance from the load, the pivot, is the load arm. So because the load arm is longer than the effort arm, we use more effort to overcome the load. It's because the load arm is longer than the effort arm. The load arm is longer than the effort arm. You try to compare the distance from the load, which is the fish, up to the pivot. That's the load arm. Then the effort arm is just from pivot to effort. Even a spade, the load arm is longer. Load to effort, or no, load to pivot, that is load arm. Then effort to pivot, that is effort arm. So when the load arm is longer than the effort arm, we use more effort. When the load arm is longer than the effort arm, more effort is used to overcome the load. And that's the disadvantage. Then we have the advantage of using third class levers. And the advantage of using third class levers is that it moves through a shorter distance. The load moves through a shorter, no, the effort moves through a shorter distance because the effort arm is shorter than the load arm. Another question: what is the advantage? What is the advantage of using third class levers. What is the advantage of using third class levers? The effort moves through a shorter distance. The effort moves through a shorter distance. The effort moves through a shorter distance. And that's why the effort arm is shorter and the load arm is longer. The effort arm is shorter and the load arm is longer. So, if the effort arm is shorter, that means that the effort moves through a shorter distance. And that's the advantage of using third class levers. And we say third class levers, we use more effort to overcome the load, NB. In third class levers, more effort is used to overcome the load. More effort is used to overcome the load, and that is the advantage. That is a disadvantage actually. So we move straight to the law of levers or principles of moments. The law of levers. The law of levers. The law of levers is also known as principles of moments. Principles of moments or the law of levers. And the law of levers states that the load force multiplied by the load arm is equal to the effort force multiplied by the effort arm. It states that the load force states that the load force multiplied by the load arm is equal to the effort force multiplied by the effort arm. As simple as that. It states that the load force multiplied by the load arm is equal to the effort force multiplied by the effort arm. That is the law of levers. It states that the load force multiplied by the load arm is equal to the effort force multiplied by the effort arm. I repeat, the law of levers states that the load force multiplied by the load arm is equal to the effort force multiplied by the effort arm. It also states that clockwise moments are always equal to anti-clockwise moments. It states that clockwise moments are always equal to anti-clockwise moments. It states that clockwise moments are always equal to anti-clockwise moments. That is the law of levers. So you can either say the load force multiplied by the load arm is equal to the effort force multiplied by the effort arm, or you say it states that clockwise moments are always equal to anti-clockwise moments. So we're going to look at an example. We're going to look at an example. I want to do some mathematics in science. You know, science and mathematics are very close friends. Science and mathematics are close friends. So we shall say a man weighs 60 kilogram force. Examples. Example 1. A man weighs 60 kilogram force. Full stop. He sits. He sits 2 meters. He sits 2 meters from the fulcrum. Or pivot of a seesaw Full stop. A man weighs 60 kilogram force. He sits 2 meters from the fulcrum or pivot of a seesaw. Then, how far from the fulcrum will the boy? That's my question. How far from the fulcrum? How far from the fulcrum will a boy who weighs 30 kilogram force? A boy who weighs 30 kilogram force sit in order to balance the man. In order to balance the man. That is the question. That is the question. A man weighs 60 kilogram force. A man weighs 60 kilogram force, full stop. he sits 2 meters from, he sits 2 meters, he sits 2 meters from the fulcrum or pivot of a seesaw. How far from the fulcrum will a boy who weighs 30 kilogram force sit in order to balance the man? So this is what we are going to do. I want to draw a seesaw. I want to draw a seesaw, and we shall put the pivot. Remember, you've been told a man who weighs 60 kilogram force. So there is a man with a boy. There is a man and a boy. So you write here man, then you come here and write boy. Okay. Then you are told a man weighs 60 kilogram force. This man is 60 kilogram force. A man weighs 60 kilogram force. He sits 2 meters away from the pivot. This is a pivot. This man sits 2 meters away from the pivot of a seesaw. How far from the pivot will a boy who weighs 30 kilogram force? This boy weighs 30 kilogram force. So how far from the pivot will a boy who weighs 30 kilogram force sit in order to balance the man? So this boy, how far? So we're supposed to find out the distance. How far from the pivot will a boy who weighs 30 kilogram force sit in order to balance the man? We go back to, so this is how we begin. We'll finish interpreting the question, then we come to the activity. Now we look at, we write the formula, and which formula are we going to write? We are using the law of levers, and this law of levers states that the load force multiplied by the load arm is equal to the effort force multiplied by the effort arm. Can be summarized like this. The load force multiplied by the load arm is equal to the effort force multiplied by the effort arm. As simple as that. Then we come and substitute. Load force is 60 kilogram force. 60 kilogram force. Our load arm, remember we said load arm, the distance between the load and the pivot. So our load arm is 2 meters equals to effort force is 30 kilogram force times effort arm, which we don't know. We can put there y, meters. So we shall substitute and say 60 times 2 is equal to 30 times y. 30 times y. 60 times 2, this is 120 equals to 30 times y is 30y. How do you find the value of y? We divide both sides by 30 by 30. 31, 30 or 1. Then 0 cancels with 0, 3 here, 1, 3 here, 4. That is 4. Then therefore we say y is equals to 4 meters. So this boy will have to sit 4 meters away from the fulcrum in order to balance the man. The boy will have to sit 4 meters away from the pivot in order to balance the man. We are going to do the last one. The last one, and we call it a day. Just one more. Example 2. Example 2. A boy weighing 60 kilogram force. A boy weighs 60 kilogram force, sits 2 meters away from the fulcrum of a seesaw, 2 meters away from the fulcrum of a seesaw. A girl sits on the other side. A girl sits on the other side. A girl sits on the other side. At a distance of 3 meters, away from the pivot of fulcrum in order to balance the seesaw, in order to balance the seesaw. So that's the question. Find the weight of the girl. Find the weight of the girl. Find the weight of the girl. Put a question mark. Now, a boy weighs 60 kilogram force and sits 2 meters away from the fulcrum of a seesaw. Then a girl sits on the other side at a distance of 3 meters away from the pivot in order to balance the seesaw. Find the weight of the girl. What do we do first? We first draw the seesaw. We first draw the seesaw. That's the first thing. You draw the seesaw. You draw the seesaw. And the seesaw will only be complete if it has the pivot. So this is a pivot. Now, we are told we have a boy. You write here boy. Then a girl sits on the other side. Girl. We are told a boy weighs 60 kilogram force. 60 kilogram force. And sits 2 meters away from the pivot. A girl on the other side, at a distance of 3 meters away from the pivot in order to balance the seesaw. Find the weight of the girl. So we are supposed to find the weight of the girl. This weight of the girl, we can give it G. So we are supposed to find G. We shall first state the law of moments or the law of levers, which says load force multiplied by the load arm is equal to the effort force multiplied by the effort arm. What is our load force? 60 kilogram force multiplied by the load arm. The load arm is 2 meters, is equal to, our effort force is G. G times multiplied by effort arm, which is 3 meters. Then we substitute and say 60 times 2 is equal to G times 3. 60 times 2 is 120 equals to 3G. 120 equals 3G. How do we find the value of G? We divide both sides by 3 by 3. 3 here 1, 3 here 1, 3 here 1, 3 here 4, 0. Therefore, G equals to 40 kilogram force. Remember, we are finding the value of G. That's the weight of the girl. So the girl will weigh 40 kilogram force. So that is how we calculate the law of levers. We use the law of levers to calculate this. As simple as that. Otherwise, thank you so much for being attentive. May the Almighty God bless you abundantly.